So later on in the lab, we'll do the redox lab. That should be a lot of fun for you. Nothing like doing some fun chemistry on a Saturday morning. But for lecture today, we'll do chapter 7, which is on quantum theory in a nutshell. It's on quantum theory. And it sounds complicated. I'll try not to make it too bad. But it's actually one of my favorite chapters because I sort of did research that utilized some of the concepts of it. So I'll try to share a little bit of that with you later on. Okay, so part of chapter 7 includes, let's see, properties of light. Is it a wave or a particle? I was waiting in line at a Carl's Jr. at one point years ago, and I heard a couple of physics majors having this discussion. Actually, it was more like an argument. It was kind of funny because the answer is it's both. But anyway, we'll talk about quantum theory. Really, what chapter 7 is also about, it's sort of about a history of the development of how we view electrons within atoms. So we'll discuss the photoelectric effect, and what the importance of that was. Bohr's hydrogen atom, wave-like properties of electrons, and quantum mechanics. It sounds complicated, but rest assured, it's not going to be like solving like these wild mathematical relationships that are behind it all. And then we'll talk about atomic orbitals at the end. Okay, so we won't get through all this today, but we'll get a good way through it. Okay, so I mentioned light being a wave or a particle. So let's talk about waves just for a moment. A wave is just vibrating disturbance in which energy is transmitted. So think of light. Every time you experience light, like right now I'm getting hit in the face by the light from the projector. I'm getting hit with photons of light. Dare I say the word photons, but we'll discuss how that works in about momentarily. So think about a ray of light hitting you, and sometimes the wave travels in a certain frequency or amplitude, and then other rays of light hit you with a different amplitude or frequency. Okay. So the amplitude of light is just if you drill a line through the middle of the wave front, the amplitude is just the height of the waves, whereas the amplitude is the height of the waves. There's something also called a wavelength, and the wavelength is the distance between the waves. Okay, and so some rays of light have a shorter wavelength, other rays of light have a longer wavelength. Okay, and the wavelength, it turns out, determines the color of the light. So longer wavelengths will have a different color of light than shorter wavelengths, okay, and so on and so forth. Now, the wavelength affects the color. What affects the brightness, though, is the amplitude. So the more amplitude within the wave, the more bright the light is. So just to demo something, I used to do this with a laser pointer, but one of my laser pointers broke. So I can't do the laser pointer anymore. But if you, maybe Austin, maybe you can kill the lights back there just for a moment. And this will be enough, just to get some shade in the room. So here's one flashlight I have. How many of you like flashlights? I don't know why, but I love flashlights. Maybe it's because I used to go camping when I was a kid, and you have flashlight wars, and you blind each other in the eyes with your flashlights, and whoever has the brightest light wins the flashlight war. And whoever has the brightest light means that they have the highest amplitude of light. Okay, of course, when I was a kid, I didn't think about amplitude, but just saying. But here's one ray of light. I'll just put it on the wall there. I could hit you in the face with it; it'd probably be okay, but that wouldn't be very nice. And then here's another flashlight. All right, what do you think has the higher amplitude? The one on my left hand, or the one on the right hand? The one on my left, right? So just to put on the board, man, that's bright. Okay, so I think this one in my left hand shines at about 300 lumens. This one's a lot less. And they're both powered by 3 AAA batteries. So the power source is the same. Now check this out. You think size matters? Okay, here's a bigger flashlight. Here's a little smaller flashlight. But this one's really cool because it hang on, this writing's kind of. All right, I guess this one's not going to work. Oh, there we go. This one kind of. Yeah, maybe the battery power is getting low. Yeah, okay. This one is really cool because it's pretty bright, but it. I think the battery's low on this one. That's what's going on. Because I know when it's maxed out, this little one wins over the big one. But little ones are great because when you go backpacking, they're little, and then you can carry less weight. All right. Anyhow, so it's all about amplitude with flashlight wars. Austin, maybe put the lights back on. All right. So your instructor has just shown a demo showing 2 different intensities of light. Draw a wave for each intensity of light you observe such that they would have the same x values on the graph. Okay, so for my blinding flashlight versus the softer light. So for the softer light, maybe have an amplitude like this. And then for the brighter light, what do you think it would look like? Maybe the same wavelength. Maybe the same wavelength, but a much higher amplitude. Right? So I'm kind of matching the waves together. Okay. All right. So the same power source, but now I think what it is with this brighter flashlight, they've designed it so that it tends to collimate the light more. In other words, all the rays of light are said to be in phase. They all have the amplitudes tend to be additive. So we'll talk about that a little bit more when we talk about interference. But anyway, that's just the nature of light. You have amplitude, which incurs the brightness, and you have wavelength, which tells you the kind of color. Okay. So the speed of light, the letter that they use for the speed of light is the letter C, italicized, and that relates the wavelength of light to its frequency. Okay, so you have this relationship: frequency is equal to wavelength. Speed of light divided by its wavelength. All right, you got these weird symbols you may not have seen before, but lambda is the term here. L-A-M-D-A, lambda. Lambda is equal to the wavelength of light, which is typically in nanometers. So here's your scientific notation, metric system coming back again and again, right? So nanometers is how many meters? It's 10 to the 9th nanometers are in 1 meter, right? So nanometers are a pretty small measurement. Frequency is in units of per second. Another unit of per second, sometimes they use the word hertz, okay, for frequency. And then the speed of light is 2.998 times 10 to the 8th meters per second. That's the speed of light in a vacuum. So when they talk about light years, like they say, oh yeah, we found a star or a planet that is so many light years away. That's how many years it would take light at this speed to reach that location. Right? That's what they're talking about. So if you even have 1 light year away, okay, that's far away because light travels really fast. Right? So if it takes a year for the light to get there at this speed, it's far away. Okay. So the frequency of light is the number of amplitudes that pass through a plane of space in 1 second. Okay, so you might notice how if the wavelength of light gets shorter, the frequency gets higher. Right? In other words, which light has the more wavefronts? So here's one wavelength. Here's another wavelength. Okay, which one has the higher frequency? Bottom one, right? It has more wavefronts passing in the same distance. All right, so that's that. So higher frequency light also means shorter wavelength. Okay. this just to relate it to our everyday life. Here is the electromagnetic spectrum. Now, if you look at the very top scale, okay, you've got wavelength, and as you see, the wavelength gets bigger and bigger and bigger as you go to the right here, but the frequency gets shorter and shorter and shorter, okay, or smaller. So higher energy light has a shorter wavelength but a higher frequency, right? Because they're inversely related. All right, so let me just say that again. Shorter wavelengths, higher energy. Also, shorter wavelength, higher frequency. So you can say then higher frequency, higher energy. Okay. And there's relationships we'll discuss from here, mathematical formulas. What we can see with our naked eye is actually quite small relative to the rest of the electromagnetic spectrum. We can only see this little sliver of light within the electromagnetic spectrum. Okay, so if you took this little sliver of wavelengths that we can see and blew it up, okay, you would have this. So we can see roughly anywhere from blue to red, but when you get towards the blue, it's really hard for us to see that. And below 400 nanometers, you get into the ultraviolet region. Okay, so that's this region here. Even further to shorter and shorter wavelengths, you get to X-rays. Those are even more harmful to us if we absorb them. This is why when you go in and get an X-ray, they cover whatever body parts they don't want to take a picture of. And then, of course, gamma rays are even more energetic rays, even still. And if you wanted to become the Incredible Hulk, this is what you want to take in, the gamma rays. Okay. On the other side of that, okay, so you go through the visible region again. Green is right in our wheelhouse. We have chromophores in our eyeballs that will absorb green light quite strongly, and so we see green light the best. Okay, and then you get to longer and longer wavelengths, and you start getting towards the infrared region of the spectrum. And again, we don't see infrared light very well, but I think dogs see infrared light better than we do. All right, so here's your infrared. You got microwave light, even longer wavelengths still. We use it to cook our food. Okay, and of course radio waves, that comes from our radios, cell phones, things like that. All right. So these are long wavelengths, much less energy, much less harmful, although there are ongoing studies to study if ongoing exposure does harm us. So stay tuned. It might be that 30 years from now, we might all realize that holding our cell phones to our heads or having it in our palms all the time gives us cancer, but we'll see. We'll see what happens. In the meantime, talk on. Okay. Okay, so again, we can only see this region of the light, but there's a bunch of stuff, shorter wavelengths and longer wavelengths that we can't see. So, oh yeah, just point out one more thing. So again, longer wavelengths are towards the red, shorter wavelengths are towards the blue. All right. And again, which energy is more, or which wavelength is more energetic? Is red light more harmful to you, or is blue light more harmful to you? Yeah, blue is more harmful to you because, again, the shorter the wavelength, the higher the frequency. It's more wavefronts hitting you per second. So here's a sample problem with that. A light wave has a frequency of 4.68 to the 14th per second. What is its wavelength? What would be the most likely color of light? All right, so how do we do this? So I just showed you an equation. Okay, what's the only one we've done so far? We know that frequency is equal to C over lambda. Okay, and rearranging this says, what is its wavelength? So let's do a little bit of math. How do we solve this for wavelength? Lambda is equal to what? Yeah, C divided by frequency. All right, so lambda would then be equal to 2.998 times 10 to the 8th meters per second, all right, divided by frequency that it gave us, which is 4.68 times 10 to the 14th per second. Also, though, it says, what is its wavelength? What are the typical units of wavelength? Nanometers, right? So we're actually going to want to convert nanometers to meters, and so what's my metric conversion ratio for that? So nano is 10 to the minus 9th. So we can say that there are 10 to the minus 9th meters in every 1 nanometer. So you remember flipping the powers of 10 and all that stuff? All that stuff you were supposed to learn last semester at the very least, but maybe you don't remember. Or maybe you were never taught, which I taught you earlier, so hopefully you remember. So we have meters canceling, we have seconds per seconds canceling as well, and we should get a unit of nanometers. All right, so you do that, and you should get something like 640.598 nanometers. Going by sig figs, though, how many sig figs should we have?
3.
Yeah, 3. So this would round down to what?
641.
Yeah, 641, right? So So 641 nanometers, what color of light would that be? Yeah, it kind of be like, if you go back to this previous slide, 641 is going to be somewhere in the red, right, or orangey red. 641 will probably look mainly red, right? It'd have to be below 600 to look somewhat orangey. So it will look, it'll look red. If you, how many of you have ever used a laser pointer before? Like a red laser pointer, you know what I'm talking about? Every laser pointer usually has the wavelength range printed on it. And look at the wavelength range, and you'll see that it's around 640 to 660. All right, so there you have it. Okay. Okay, so in the 1800s, classic physics predicted that substances can emit light or absorb light in any arbitrary amount. All right, but what they found in experiments back in those days is that when they heated objects up and they observed the light coming off of them in the dark, that the light coming off of these heated quote-unquote black bodies, which is basically a hot metal rod or some kind. And then what they observed was that when light came off of these objects, when they heated them up to be really high, let them cool down. As they're cooling down, light's coming off of them in discrete colors rather than just as like a white light. And so scientists back then, of course, couldn't explain this. And so like, oh, that's interesting. Why is that happening? So around the turn of the 20th century, Maxwell Planck, around the year 1900, proposed that light coming from a heated black body emitted energy in discrete quantities, the smallest of which he called quantum. Okay, and so that was the first time quantum was ever used in science. So, and the quantum referred to just discrete quantities of light, okay, coming off. And then from 1900 to 1926, the idea that the energy of light was quantized extended to microscopic systems and is the fundamental idea of quantum mechanics. So quantum mechanics wasn't really born until the 1920s, but this is sort of prelude to that. So Planck's quantum theory related the energy of light to its wavelength. Okay, so he came up with this equation. Energy of the light wave is equal to hc over lambda, where h is what we call Planck's constant, and Planck's constant is 6.626 times 10 to the minus 34, and the units are joules times seconds. And always remember that energy always has units of joules. So when you talk about light, what's the energy of light from its wavelength? Well, you have to have joules in there somewhere. Right? So here's another example. X-rays have a wavelength of 45.2 nanometers. What is the energy of X-ray light in joules per photon and in kilojoules per mole? So we'll, cool. Okay, so the equation is E light rhymes with D light, okay? It's delightful mathematics, okay? That's equal to HC over lambda. So Planck's constant is 6.626 times 10 to the minus 34 joules seconds. Speed of light in a vacuum is 2.998 times 10 to the 8th meters per second. And all of that is divided by lambda. Okay, and so what is lambda in this problem? 45.2 nanometers. Okay, so if you look at the units, we got meters, we have nanometers. So again, we're going to have to convert from nanometers to meters. How do we convert from nanometers to meters? Same as over there, right? But it's actually going to be reversed, right? Reversing the units we had there. So it is 10 to the minus 9th meters for every 1 nanometer. All right, there's only 1/1000th of a meter in a nanometer, right? Really small. So the meters then cancel. The seconds here will cancel the per second here. You might have forgotten, but when you see a unit with a negative exponent, it means it's in the other in the denominator. Okay, so per second cancels out seconds, and you get joules. All right, so do me a favor and just punch that in your calculator and tell me what you get. So 4.39 times 10 to the minus 18th joules. And this one says it wants the energy of light in joules per photon. So it's understood that when you're calculating this light, it's the energy in a single photon. Right, so it's already actually unsaid, but it's there. It's joules per photon. Did anybody not get 4.39 times 10 to the minus 18th? Just curious.
I got to the 19th.
You got to the 19th?
Yeah.
So if you get to the 19th, it means you're probably adding in a times 10 into your exponent key. If you're off by 1 order of magnitude, you would punch in 4.52 e to the minus 9th, not times 10 e to the minus 9th, for example. That's probably what you're doing, I'm guessing. So if you're off by 1 order of magnitude, again, the reason why I asked you to punch it in was because even in this class, I've seen students still, after a year, don't know how to use their calculator. All right, so make sure you know how to use scientific notation in your calculator. Okay, I've been kind of preaching this for a while, but you know, and I even gave you a problem on the exam, first exam, asking you, show me how to use your calculator, and some of you still got it wrong. And I'm like, you know, it's Chem 107, you should have learned that from Chem 107. Okay, same thing with here. So here's what happened probably. So you have like a times 10 here, a times 10 there, and a times 10 here. You probably had an extra times 10. Did anybody get some weird exponent that's way off? No? Okay, good. So that means you still remember how to use parentheses in the denominator? Okay, good. Okay, so that's in joules per photon, and it asks, what is the energy of X-ray light in joules, kilojoules per mole? So if we take this answer, we could say, okay, 4.39 times 10 to the minus 8 joules over photons, or per photon. And to get to kilojoules from joules, what do we have to do? Yeah, so there's 1,000 joules in a single kilojoule. And then it has here kilojoules per mole. Well, how do we get per mole? Avogadro's number. So we can say that there are 6.022 times 10 to the 23rd photons per 1 mole of photons, all right, per mole. So the photons then will cancel. So we'll have units of kilojoules per mole of this. All right, so that would give 2.65 times 10 to the 3rd kilojoules per mole. So you can see how Avogadro's number can be assigned to anything that's too small to count, right? It was atoms per mole, it was ions per mole, molecules per mole, now it's photons per mole. Something to point out too, 4.39 to the minus 18th joules. Does that sound like a lot of energy to you? It's very, very little, okay? But it's only for 1 photon. What if you were hit by a mole of photons? Okay, that's when you would be hit with this kind of energy here. So it'd actually be 2,650 kilojoules hitting you if you absorbed a mole of photons. All right, so just to give you some scope, right? One photon has very little energy, but when you walk outside and get hit by the sun, how many photons do you think you're getting hit by? Like quadrillions and quadrillions of photons are hitting you in the face when you walk outside, right? And that's why you're feeling all this heat when you stand in the sun, because it's not just one photon hitting you, it's like quadrillions and quadrillions and quadrillions hitting you, right? And so that's why you feel heat from the sun when you walk outside. So I mentioned the word photon, and it's kind of a Freudian slip. It's been a Freudian slip until now. We're not supposed to know the word photon yet. And the reason why is because back in Maxwell Planck's day, they haven't quite done the photoelectric effect quite yet. But a few years after Maxwell Planck came up with his quantum idea, they did an experiment around 1905 called the photoelectric effect. Okay, and the photoelectric effect, what it showed was that light not only had wave-type nature to it, but it also had particle nature to it as well. So just to describe the experiment to you, what they did was they took some light source, and back then they had